Hello and welcome to this video where we're going to look at some questions and answers on the magnetism and electromagnetism topic. So let's get started. So in this first question, a student has set up an experiment to investigate the magnetic field around a current carrying wire. We need to describe how the student could use this experiment and a compass to investigate the magnetic field produced by the wire. So what do we need to do? Well, number one, they're going to place the compass onto the card. So they're going to be placing it here. They're then going to observe the direction the compass points. And when they've done that, they're going to plot and draw that line. Once they've done that, they'll then move it around into different locations. And they can also consider different distances. Okay, question 1b. Draw the shape of the field which will be found around this wire. Well, we know that in this example, the field is going to be a circular field around the wire, like so, with the wire running through the middle. Now, as well as this, we need to give the direction. For this, we're going to use the right hand rule. So we get our right hand and we make a thumbs up symbol, like this. We then need to consider which way the current is travelling. So here you can see in the diagram that it's showing that it's going at the top and down the bottom. So we need to rotate our thumb and so that it travels in the direction of the current, which is down. And then when we look at which way our fingers are pointing, you can see they're moving around here in a clockwise direction. So our arrow lines are going to show that the magnetic field lines are moving in a clockwise direction. Part C. The behaviour of a magnetic compass is evidence that the core of the Earth is magnetic. Explain why. Well, a compass will always point to magnetic north. And this is because it's lining up with the Earth's magnetic field. Okay, on to the next page. In this question, two students A and B are using different methods to see magnetic field patterns. Student A is using a compass to plot a magnetic field pattern. We need to describe how they could do this, and we can draw a diagram. So what the first thing we're going to do is we're going to place the magnet on a sheet of paper. So we've got our sheet of paper with our magnet on. Then we're going to place the compass near the end of the magnet, like so, and we're going to mark a position where the needle points. We're then going to repeat this for different locations around the compass. In this question here, we need to sketch the field pattern that the student would find around the bar magnet. Our sketch should show the direction of the field pattern. So when we're drawing our lines, we're going to draw a couple of lines on each side, like so. We can even have some lines coming in and out. We also therefore need to draw the arrows. The arrows for a direction of a field pattern always travel from the north to the south. So it's going away from the north towards the south. So they're going to look like this. In C, it tells us that two students have investigated the magnetic effect of a current carrying wire. Look at the graph at their results. What is the trend shown by the graph? Well, for the first mark, we always want to use the axes title. So as the distance from the wire increases, the magnetic field strength decreases. And we can see this because it's got a negative correlation. How are we going to pick up our second mark? Well, looking at this, we can see that it decreases in a non-linear pattern. What I mean by that is it's not a straight line for decline, it's this curve where it decreases rapidly at the start and then starts to slow down as it levels off. Okay, on to the next page. In this question, our figure shows the magnetic field produced by a current in a long straight wire. Which row of the table is correct when the strength of the magnetic field is greatest? Well, let's have a look. So when it's at its greatest magnetic field, the distance is going to be small and the current is going to be large. So it can't be this one. It's going to be that one. We can check our other ones. So we therefore know the correct row is B. Which of these materials would be the most suitable for making a temporary magnet? A temporary magnet needs to be a magnetic material, and the only magnetic material that we've got there that would lose its magnetism easily would be iron. Steel, which is made a majority of iron, will hold its magnetism quite a long time, so it wouldn't be a very good temporary magnet. And finally, the last one, this figure shows a magnet holding some paper clips. Describe how a student can show that the paper clips are induced magnets. Well, induced magnets only have magnetism when they're within another magnetic field. So the way that we would do this is we would remove the magnet from the paper clips and they would no longer attract each other. As this paper clip here, for example, is only attracting this one because it's becoming a temporary magnet, an induced magnet, because it's within the magnetic field of this magnet, this permanent magnet. So if we took the permanent magnet away, this magnet would no longer be within that magnetic field, which would no longer be acting as an induced magnet, and therefore would not attract the second or the third paper clip. Okay, let's move on to our next question. Okay, so in this question we're looking at a solenoid, which is this coil of wire here, and we've got some information about the solenoid. We need to draw lines on the figure below to show the shape of the magnetic field just within the solenoid. So within the solenoid, our magnetic field is strong and uniform. So we're going to draw nice parallel lines, roughly evenly spaced out, going through the middle of our solenoid. We don't have to worry about what happens outside because it's only asking us for the magnetic field inside the solenoid. How could a student determine the shape of the magnetic field around the solenoid? Well, they could do this in exactly the same way that we've done previously. So they would place a compass on card and draw the direction the compass is pointing, and then again you would repeat that for different locations. Nice quick page. Let's swiftly move on. So here the student is investigating the magnetic properties of 3 rods. So each rod is made of one of the following materials. So we've got soft iron, steel and wood. They place each rod within the solenoid, they connect it to the power supply, and they test the magnetic strength by seeing how many paper clips it can pick up, which we've got here. You can see before, when there's a current, and then 1 minute and 10 minutes after the current is switched off. We need to complete the table to show which material each rod is made from and give the reason why. Part of the table has been done for us, so let's use information from the table above. So rod A, we can see that tells us it is not magnetic. So when we're looking at R3, we've got soft iron, steel and wood. It's quite clear that A would be made from wood, as the other 2 are magnetic. Now we've got a decision to make about the others. So when we look at B and C, so we're looking here in our table, we can see that both of them do pick up paper clips when they're within, when there's current within the solenoid. So it could be either of those 2. Now the key thing is what happens afterwards. You can see that 1 minute afterwards, this one only has 1, whereas this one has 7. And after 10 minutes, B has lost everything, every paper clip, whereas C still has 7. So C is holding on to the electromagnetism longer than B. So soft iron can very quickly lose its magnetism, so that will be B, whereas steel which holds the magnetism for a lot longer after the current is turned off, must be C. So we can write for a reason, the soft iron only attracts paper clips when there is a current, whereas the steel attracts when there is current, but also after. In our next example, we've got a magnet producing a magnetic field, which diagram shows the magnetic field pattern around a bar magnet. Tick one box. Well, we know that the magnetic field is always strongest near the poles, so it's going to be nice and close together, the field lines near a pole, so we know it's definitely not going to be one of these two. And then we need to decide between these. Now, the only difference between these you can see is the arrows, and so we need to think about which way the arrows go. Remember, the arrows always go from north to south. So if we look at these arrows here, we can see that they're the wrong way round, meaning the only one that's left that's correct is this one, from the north to the south. That's where those arrows are going. This diagram shows 3 metal blocks, so we've got our 3 metal blocks here. They're not labelled. One of them is a permanent magnet, one of them is iron, and one of them is aluminium. So how could we use another permanent magnet to identify each of these blocks? Well, we'll start off with the aluminium. So aluminium isn't one of our 3 magnetic elements, iron, cobalt and nickel, so therefore we know that the permanent magnet would not be attracted to it. So aluminium is not attracted to the permanent magnet. Next we could do the iron. So the iron one will be attracted to the permanent magnet. And then we can do the permanent magnet, which will be attracted just like the iron, but to be able to tell the difference, it will also have an opposite pole, and so it will be repelled by the permanent magnet. So to make it really clear, for our iron, it will only be attracted to the permanent magnet. So the aluminium won't be attracted, the iron will only have a force of attraction, and the permanent magnet will have both a force of attraction and a force of repulsion. So our final question is the 6th marker here. The diagram below shows a toy crane. The toy crane uses an electromagnet to pick up and move the blocks. Explain how this electromagnet is able to pick up and move the blocks. So electromagnets obviously can be turned on and off with electricity, and that's the key thing here. So we could talk about points. So for example, if we turn the circuit on, this will turn the electromagnet on. There will be current in the coil of wire. So this will produce a magnetic field. The iron core will therefore become magnetized. And so the blocks will be attracted to the magnet. And then by moving the crane, the blocks will also move. And then finally, just to finish up, to drop the blocks, turn the circuit off. And that's been plenty of marks to get us our 6 marks. So hopefully you had a go at answering those questions and you can see anything that you've missed out. Check out our other videos on electromagnetism and our other questions. Make sure you subscribe, and as always, happy sciencing.